Okay, this is section 2.2, limits involving infinity. I think the biggest piece with this is understanding that infinity isn't a number. So before we can go on and talk about limits that involve infinity, I'm going to give you a second. Go ahead and hit pause and read the objective, read this little paragraph here and this paragraph here. When you're done, come on back. Okay, so in this class, we are going to have limits that actually show the notation equaling infinity sometimes, but as you just read, since a limit is a y value can never equal infinity. It's just notation that we're going to be using, and it is something that the AP accepts. So we're going to use that. Let's go ahead and look at, there are two examples that show up quite frequently in calculus. The first one is dealing with the function sine of x divided by x. And this is something that we're going to use our graphing calculator to show us what this looks like. When you do that, go ahead and type sine of x divided by x into your y1 on your grapher. I would point out that you need to make sure that you close the parentheses around the x. So again, you will have the sine of x, close that parentheses, divide by x, and this is what's going to go into y1. Okay. We did this in the previous section in 2.1, but let's go ahead and show what that graph looks like. It's kind of bouncing around here, and then it goes like this, and then it comes back down. It looks something like that and goes on forever. Okay. The first limit that we're going to look at in part A asks you to look at the limit as x approaches 0. So as we get closer and closer to 0 from the left, and we follow this function, or as we approach it from the right, you'll see that it's approaching the same number. You can confirm this both graphically, you can confirm it numerically by looking at the table, but these the limits from left and the right agree, so we are getting out a value of 1. Now, as you look at the next part, part B, it says, what is the limit as x approaches positive or negative infinity? What this is essentially asking us is to ask ourselves what happens to the y values as we get further and further away from the origin. And it's bouncing back and forth, and as we get further and further away, it appears to be getting closer and closer to the x-axis. You can zoom out and see that this does occur. You can check your table of values and get further and further away from the origin. You're going to see that those decimals get very, 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 very small. Okay, so this limit equals 0. This particular function, sine of x divided by x, shows up several times throughout the course, so this is something that you're going to need to memorize, either what the graph looks like so you can evaluate the limits quickly, or just evaluate the limits by memorizing them. Okay. The next example, example 2, is dealing with a rational function. The function is y equals 1 divided by x. And in the previous section, we talked about evaluating limits algebraically. This is x approaches a constant. We would say plug it in, substitute it. If we do that, we're going to get 1 divided by 0, which isn't allowed. There's nothing to factor, conjugate, cancel. Nothing that we can do is going to help us remove that 0 in the denominator. So that tells us we have a vertical asymptote going on at x equals 0. And if you remember this function from pre-calculus, it's kind of like the bow tie, sideways bow tie, butterfly shape, however your teacher described it or however you described it. But what happens is, on the right-hand side of 0, as you get closer and closer to 0, you're taking 1 and you're dividing it by a smaller and smaller and smaller positive number. 1 divided by a very, very small positive number is a very, very large positive number. So from the right-hand side, we've got values that are approaching positive infinity. So the limit as x approaches 0 from the right of 1 divided by x, even again, here's our equal sign, but we don't really mean equals. We're saying that the numbers are getting infinitely large. You'll notice from the left-hand side of 0, however, you're taking 1 and dividing it by numbers that are getting smaller and smaller and smaller, but they're negative. And when you take 1 and divide it by a very, very small negative number, you get a very, very large negative number. The left and the right-hand sides do not match. Therefore, the overall limit of as x approaches 0 of 1 divided by x does not exist. On this function, as you get further and further away from the origin, as you approach positive or negative infinity, the y value is getting closer and closer to 0. Okay, it doesn't matter if you're approaching positive or negative infinity, the y value is approaching 0. So that's what our limit is for this. And again, this is these two examples, examples 1 and example 2. You are required to know them by heart, either what the graph looks like so you can evaluate the limits, or just by figuring them out. Okay, now in your pre-calculus class, you may have discussed horizontal asymptotes. Maybe you only got as far as drawing a graph that had a horizontal asymptote. Maybe it was an exponential function or a logarithmic. But I think the key thing is to point out, if it's a horizontal asymptote, it can be crossed. And, perhaps one part of the graph approaches this line and the other part of the graph does not. A horizontal asymptote just basically is asking us to find out what happens to the function values as x approaches either positive or negative infinity. And it could be two different values. But the idea is, if there is a horizontal asymptote, then there is a limit value to this problem. Okay, so we want to know what happens to y as x gets further and further away from the origin. Okay, so what happens to those y values? If there is a horizontal asymptote, there will be a limit. It's supposed to say moves. So what happens to the y values as x moves away from the origin? That's a horizontal asymptote. Okay, so I want to know the y values as x moves away from the origin. Now, a vertical asymptote is kind of going to flip that limit notation around. For a vertical asymptote, this is something that's a little bit different in the sense that a horizontal asymptote you may cross with your graph. A vertical asymptote cannot be crossed. You only have two options when you approach a vertical asymptote. Your function goes up, or your function can go down. Those are your only two choices. So it's an x value at a vertical asymptote. So there is a specific constant value. So we're talking about the limit as x approaches some value of the function, and the y values are going to go very, very large in either direction. Maybe both positive, maybe one positive, one negative, maybe both negative. But either way, again, as you approach a vertical asymptote, you only have two choices, up or down. Okay, we just did this example on the previous page, but I'm going to take it from a fresh approach here and do this algebraically. As x approaches 0 of the function 1 over x, what is the limit? I would ask you to substitute this in, and again, if you try to substitute, you're getting a 0 in the denominator. This is such an important example and such an important concept, that's why I put it in the notes again. Anytime you get a 0 in the denominator that you cannot remove, it means you have a vertical asymptote. And again, your choices are either up towards positive infinity for the y values or down towards negative infinity for the y values. All you have to do is determine, are the values positive or negative, okay? Because we know it's going to be an infinity value. So anytime you come up with a 0 in the denominator that you can't get rid of, I'm going to ask that you separate this into a left and right hand side limit. And algebraically, because you've already determined that it's either going to be a positive or a negative infinity, you're just going to think conceptually now, and that's hard for a lot of students to do. They want to plug in numbers and get an actual value. But again, you're getting either positive or negative infinity out. And I'm sorry I keep repeating myself, but you need to understand that. So let's take a look as x approaches 0 from the right. If you plug in positive values just to the right of 0, you are plugging in positive very small numbers. 1 divided by very small positive numbers is a very large positive number. Likewise, from the left, if you plug in a number just to the left of 0 for x, you're taking 1 and you're dividing it by a very, very small negative number. 1 divided by a small negative is a very large negative number. Because these guys from the left and from the right do not equal each other, this overall limit does not exist. Okay? Moving on to example 2. Here we've got x approaches 2 of the function 1 over the quantity of x minus 2 squared. If you try to take x and plug it in and substitute it, you're again getting a 0 in the denominator. There's nothing that this can cancel with, so that's telling us at x equals 2, you've got a vertical asymptote. Sometimes it might be helpful for you to write that down so you remind yourself, if you're approaching a vertical asymptote, you only have two choices, positive or negative infinity for your y values. So you're going to split this up just like we did in the previous example. Limit as x approaches 2 from the left of 1 over x minus 2, the quantity squared. And the limit as x approaches 2 from the right of the quantity, or of 1 over the quantity of x minus 2, quantity squared. Okay? Again, think conceptually here. Let's look at the limit as x approaches 2 from the left. Those would be values like 1.99, okay? 1.99 minus 2, order of operations here, is going to give us a negative number, very, very small negative number, but then we're squaring it. When you square a negative, you're getting out a positive. This is going to be 1 divided by a positive number. And because we pointed out before that this is a vertical asymptote and we only have two choices, positive or negative infinity, I don't care about the actual numerical values. I just care that it's going to be positive. Okay, so that's a positive infinity for that limit. Now from the right-hand side, as you approach 2, you'd be plugging in numbers like 2.001. If you subtract 2 from a value like that, you're getting a small positive number. Squaring a small positive number gives us a smaller positive number. 1 divided by a very, very small positive is a very, very large positive. In this example, we're getting them to match. Check. So that works. This overall limit is going to approach infinity. I would like you to hit pause now and please try number 3 on your own. Okay, let's see how you did. If we plug in 2 and we substitute it in and try to evaluate this limit algebraically, we're getting a 0 in the denominator, nothing that we can cancel it with. So we're going to break it up from the left and from the right. Limit as x approaches 2 from the left of that entire function. Okay, plugging in numbers 2 from the left, 1.999 minus 2 is going to be negative, but you square it and it's a positive. In the numerator, you're plugging in 1.99 or something along those lines, but it's a negative. Negative divided by a positive is going to, negative divided by a positive is going to give us, wow, this is giving me a good time here. Let's try this again. Okay, let me cancel that guy and try that again. Limit as x approaches 2 from the left of negative. Okay, we had just decided this would be a negative over a positive. So overall, negative divided by a positive is going to be a negative value. So that's a negative infinity. From the right, the limit as x approaches 2 from the right. Okay, again, negative divided by a positive, and this time we're getting out a negative infinity. Those two guys match, so overall the limit will be approaching negative infinity. How'd you do? If you got that one wrong, make sure you circle it, go back, try it again. If you're not sure why you got it wrong, make sure you ask me in class tomorrow. Now for horizontal asymptotes, you may have learned last year that you're going to look at the dominant term, whether it be a top-heavy function, a bottom-heavy function, or that it's equal and it's balanced. If you didn't discuss this last year, or if you don't remember it, I'm just going to briefly run through it with you. When x is getting larger and larger, you're basically asking yourself, what's going on with the y values as that happens? Remember, that's what the limit means. And I challenge you this. If you are talking about winning the lottery, and if you win a $200 million jackpot, and someone comes along and says, you forgot $1,000, in the grand scheme of things, that $1,000, although nice, doesn't really matter in comparison to the $200 million. And that's where this whole dominant term kind of idea comes from. We're talking about x getting infinitely large. So for a problem like this, when you're talking about x squared versus 2x versus 1, out of all of these terms, the x squared is going to grow the fastest, the quickest. Likewise, in the denominator, 2x squared is going to grow much faster and be more important than the minus 3. Okay, so what you're going to do is you are going to look at the largest exponent of x in the top, the largest exponent of x in the bottom, and you're going to compare the two of those things and ask yourself, what will happen if I'm only looking at x getting infinitely large for those values? So in this problem, problem number 1, x squared is our largest term. In our denominator, 2x squared is our largest term. Although this is not the same function, we're going to put an approximate here. This would be approximately the same as if we were to look at just the function x squared over 2x squared. Pardon me. If we were to do that, look at what happens. The x squareds are going to cancel, and you're going to end up with a 1/2, and it doesn't really matter what x is approaching. So this whole idea of estimating the limit by just looking at that dominant term, that's how we were able to come to just the x squared over the 2x squared. Okay, so this is that idea of the top heavy, the bottom heavy, or the balanced. For a problem like number 2, there's a little bit of work that has to go into it, but again, we're going to try to find the dominant term. And we're going to look at the numerator first. We've got a 3x squared, and in the denominator, we've got a 4x squared that's more important, but there's a square root involved, and we'll get to that in just a second. Because I want you to notice that this is x approaching negative infinity, so there might be a negative to contend with. This would be approximately the same as if we were to take the limit as x approaches negative infinity of only the 3x, that dominant term, and the square root of 4x squared. Now, when you take the square root of an x squared, back in algebra, we learned that the x squared would always be positive, and therefore, if you take the square root, that would always be positive. So in order to take this, the square root of a variable that's being squared and simplify it, you're just going to put absolute value markings around it. So this would look something like this. 3x, the square root of 4 just becomes a 2, and then the square root of x squared would be an absolute value of x. Now, as we look at this, we have a 3 over 2, that much is guaranteed. And we've got x over x, and those would technically cancel. However, the x in the numerator will be negative. The x in the denominator will always be positive, so we're going to account for that by putting a negative. So this is going to be a negative 3/2 limit. If you have any questions on this or anything I said, you know I talked about a little bit of algebra review, pulling out this absolute value of x. Feel free to ask me tomorrow. For a problem like number 3, where you are taking the limit as x approaches infinity of the cosine of x divided by x, this is a little harder to compare because we don't just have x, we have the cosine of x. However, we're looking for whether this is top heavy, bottom heavy, or equal. So far, we've dealt with 2 equations where it was equal and the overall limit was going towards the constant, the ratio of the coefficients. And for problem number 3, it's a little more difficult to understand, whether it's top heavy, bottom heavy, or equal. So for a problem like this, think about what happens with a cosine of a function. Because x is getting larger and larger and larger, the cosine values are going to fluctuate between -1 and 1, but they're always bouncing back and forth, -1 and 1. and they're ranging everywhere in between those values. The denominator, x, is getting larger and larger and larger and larger. Regardless of whether you are taking a -1 or a +1 and dividing it by a larger and larger and larger number, overall, this is going towards 0. And I would ask you to graph this out on your calculator and take a look as well. So for that one, we had a case of this was being bottom heavy. So that dominant term in the denominator is getting larger faster than the numerator. So anytime that happens, you're going to be dividing by a larger number, and that is always going to go towards 0. Let's go ahead and take a look at the next page. I'm just kidding, we're done. See? It went fast. All right, I'll see you guys in class tomorrow.